This is the geology news for April of 2021. And as always, I like to start out with earthquakes since that is my primary interest and field of study. So in the last month, the biggest event was a magnitude 6.6 near Antarctica's South Sandwich Island. This is a transform plate boundary here between the Antarctic plate and looks like the South American plate right here, where these two plates are spreading apart and grinding past each other. There's another interesting earthquake, which is a magnitude 6.5 aftershock up here north of New Zealand, off near the Kermadec Islands, and that's an aftershock of the 8.1 earthquake, which occurred in mid-March. There was also a magnitude 5.6 in Iran that damaged a number of buildings and caused a number of injuries, but no deaths as far as I've been able to find out. Normally, that's not a terribly strong earthquake, but this earthquake occurred at a very shallow depth of only about 10 kilometers. So there was very strong and violent shaking, even though it didn't last. And the short duration of that size of an earthquake is what prevented greater damage and deaths from taking place. Zooming into the United States here, we had some pretty typical background seismicity. We are still continuing the aftershock trends of the Bora Peak earthquake, the Monte Cristo earthquake, and the Ridgecrest sequence over here in California, as well as some fairly typical seismicity for the California San Andreas fault zone. There was a couple small earthquake swarms down here just south of the border and up here near the Mendocino Triple Junction, where the San Andreas fault meets the Cascadia subduction zone, and a lot of complicated tectonics goes on here. This is one of the most seismically active areas in North America. Also continuing from last month, there's an earthquake swarm down here at a natural gas field in West Texas. Are there any questions about earthquakes before I move on?
Yes.
Scott has his hand up, and I heard another yes. So Scott, could you go first?
You might explain probably why the natural gas field out in Texas had the earthquake.
Well, in this particular instance, not being familiar with the geology of this basin, I can't say for certain, but it is most likely related to ongoing deep disposal and/or hydraulic fracturing of gas-bearing shales in that area. A hydraulic fracturing generally occurs at too shallow of a depth to initiate earthquakes, but deep disposal wells go down far enough in the crust to dispose of fracking fluid and other brine, which is what they call the fluids they also pump up along with natural gas. And those get shoved down far enough into the crust that small earthquakes can be generated. And this is something that some of our faculty at Portland State study.
And I think I heard another question out there.
It was me.
Please go ahead.
Kentucky. When I was younger, we had one in Kentucky. Where's the fault line for Kentucky?
Well, there's faults and earthquakes can happen just about anywhere in the country, regardless of whether or not a large fault is nearby. There has not been any major seismicity in Kentucky for a little while, as far as I'm aware of.
Oh, I was 16, so that showed.
And I feel like, Andrew, maybe you did a piece maybe almost a year ago on earthquakes out on the East Coast.
Yeah, there was an interesting earthquake in North Carolina, along with a number in the Delaware, Manhattan area.
All right.
I'm going to move on to volcanoes. The fantastic and dramatic sequence in Iceland continues to amaze spectators. You can see people observing the lava flows over here. This was a shallow dike. An intrusion of lava has reached the surface in this peninsula at the southwest end of Iceland, and it has now opened a third vent, which we can see here, which is spilling lava into the nearby valleys. This is a very peaceful, gentle eruption and will most likely not cause any large disruption like we saw at Eyjafjallajökull in 2013?
Nice pronunciation, Andrew. So smooth.
So we call this a Hawaiian-style basalt flow because of its sort of gentle, fluid, slow-moving behavior. In sort of the opposite end, we had new activity at La Soufriere volcano in St. Vincent, and I'll get to that in a second. But this is the currently erupting volcanoes map from Volcano Discovery. There are 38 ongoing or new eruptions, and the earthquake swarm at Mauna Loa is not happening anymore. I guess I forgot to remove that line, but I will segue into the La Soufriere volcano. So this is what it looked like up until about a month ago. There's this nice, small, cute, round little lava dome slowly been pushing its way into the crater of La Soufriere volcano on St. Vincent in the Caribbean. However, on April 9th, it sort of exploded. There was an increase in volcanic seismicity that the local National Emergency Management Office of St. Vincent and the Grenadines detected and evacuated some 20,000 people from the north end of the island. And shortly afterward, these large eruption plumes began coming out near continuously from the volcano and are continuing today. You can see the evacuation zones here. There has been heavy ashfall and pyroclastic flows have been descending the flanks of the volcano, burying canyons in hot, searing ash. There are no known fatalities, and there are some injuries from the ashfall and dangerous air quality. But so far, it has been a success of emergency management. And large explosions are continuing even today. And this is going on for about the last 15 days now.
It's so impressive that they were able to evacuate that many people. I think some up to St. Lucia and other islands.
Yeah, they were boarding cruise ships, but there were issues because the neighboring countries didn't want to take anybody in because of COVID. So there's some logistic challenges that are going on. And not to mention ashfall is impacting other neighboring islands in the Caribbean. But so far it has been a success in that nobody has been killed by this volcano.
Can I ask, I don't know much about the underlying tectonics of that area. Is this, with the pyroclastic flows, is this a rhyolitic high silica volcano like you have at Mount St. Helens, or is it more of a sort of Hawaiian type?
So it's definitely not Hawaiian type because Hawaiian types effuse slow, gentle, very fluid basalt lavas, but this volcano, when it does produce lavas, make these big sticky piles like this. It's not a rhyolitic volcano. I believe it's in the dacite spectrum, so in the mid 60% of silica content in here, which still allows this lava to retain a large amount of gas, which can then produce these explosions.
So would Mount Hood be a better comparison, or am I?
Mount Hood would be a better comparison. This is erupting considerably larger volumes than Mount Hood is known to produce.
I see. Thank you.
So are there any other questions about volcanoes? I think Paul may have covered just about all of that.
I don't see anything.
Can I just add
Scott,
two quickies?
Please.
2 days ago, Guatemala has a volcano erupting, and the lava flow is within 2 blocks of a village that is there.
I guess I missed that one. Was that Fuego?
Yes, it was.
Yeah.
And then La Reunion, which is a volcano in the Indian Ocean. It is a hot spot. It's off the coast of Madagascar. It's a old colony, and it has been erupting last week.
I guess I missed that one too.
Yeah, and good job.
And if you're interested in those Guatemalan volcanoes, we have a great lecture from our member Bill Burgle on Guatemalan volcanoes on our website, gsoc.org, from a few months ago.
Thank you for catching those, Scott. And I'm going to move on to some of the new research that has been published in the last month or so. And the one that I found most interesting kind of combined two of my big interests, being earthquakes and volcanoes. And that was this new method for predicting the viscosity of erupting lava. So magma viscosity is very important for the style of a volcanic eruption. Very thick, very viscous lava is going to explode, like at La Soufriere. Reservoir fluid lava is going to erupt gently, like we see here in the 2018 Hawaii eruption. So researchers at the University of Hawaii and elsewhere used the earthquake sequences that were recorded before and during this Kilauea eruption from 2018. And they used these earthquakes to sort of map and model the stress that was present in the rocks at depth underground. And they've determined that high stress in rocks indicated a more viscous and explosive magma. and a low stress indicated higher effusivity, or less explosive, more fluid, gentle eruption like this one. And this is all ex post facto analysis of the data, but this does have implications for future activity, at least at Kilauea and at other very well monitored volcanoes around the world, for predicting the oncoming eruption style. Because that's one thing, volcanoes always tell you when they're going to erupt, but they don't tell you how they're going to erupt. So this method could be very interesting for determining styles of eruption going forward. And I'm very excited about that.
Sorry if I missed this. How do they measure the stress?
It goes down to calculating the amount of energy and in what direction it moved during an earthquake. These are very small earthquakes. These, I mean, they do vary from ones that are felt by residents on the island, but they are also very, very small, detected only by the most sensitive seismometers. You can calculate the energy that is released in each one and the sense of motion or how the stress is being rearranged during these events.
I see. Wow.
Gets a bit into the weeds there as far
Yeah,
as how
it's
they
interesting. So they're
model
sort
it.
of modeling it based on the seismic.
Yeah, that's exactly it.
Wow.
There is another less positive article that came out. This actually made the front page of the Oregonian a couple of weeks ago, and that was about radon in public housing. Now, radon gas is a radioactive element which is emitted by certain soil types, and it tends to leak into floors and other low-lying areas and buildings. And it is the second leading cause of lung cancer in the United States. And it's naturally occurring. And it is common up here in Portland, for example, and throughout the Willamette Valley. But less than 1/3 of public housing authorities around the country have ever tested for radon, which puts approximately 400,000 people across the country at risk. And these are dominantly low-income people taking use of public housing. Recently, about $4 million was secured from Congress to begin removal systems and studying this as a pilot project, but even that has not moved since that funding was appropriated. And it will take an estimated $49 to $78 million to test and remove radon from existing housing units. And the Department of Housing and Urban Development has been sluggish at addressing this issue for decades. And we're hoping that the new administration will start to make some progress on that, as this is a very large issue and has been ongoing for decades.
Andrew, I'm glad you brought this up. We had a presentation some years ago from one of Dr. Burns' students, I think, and maybe Scott can speak to this, about the presence of radon in the Portland area. Scott, where are we on this issue now in Portland metro area?
And we just thank all of the students, the grad students at Portland State, because they are the ones who have unlocked the secrets and distribution of radon in not only the Portland area, but also Vancouver and Oregon. And people are testing. Bottom line is, it's cheap to test and it's cheap to mitigate. And over the last 30 years, we've done a good job in getting people to test their houses. And many, many houses have been mitigated, which is good. And we're saving lives.
Are there agencies in the city or county level that are alerting people to this?
We have forums, and we try every chance with the media to get people to get out and test. The article that Andrew mentioned, this is a guy at the Oregonian who has been following this for 4 years, and he is doing a wonderful job. He's focusing in primarily on public housing and the lack of testing of a lot of these buildings, that they need to do that more.
We have a question from Kara in the chat. Where are the areas in Portland that are most at risk?
The highest areas in Portland are Alameda Ridge, North Portland. We call it Radon Ridge. And then basically coarse grain Missoula flood sediments, where you have the basalt is not a generator and a producer of very, very high amounts of radon, but granite and granitic sediments are. So if you have areas with high permeability and the generators, it has a chance of getting into the houses. So all of Clark County is very, very high at Alameda Ridge in North Portland. And then any old landslides, if you build a house either on an old fault or a landslide, you have a high chance too.
Okay, thank you, Scott. Andrew, back to you.
So that is a good issue for us in Oregon to be aware of, as well as others across the country. Moving on to another piece of dinosaur news that came out this last month was the discovery of an opposable thumbed dinosaur. And this is the oldest confirmed opposable thumb dating back to the Jurassic. This is a pterosaur Cunbingopterus antipolycatus from 185 million years ago. And it's a pterosaur, so it's a winged dinosaur. It's not a reptile. Don't call them reptiles. They're pterosaurs. It had a wingspan of about a yard, 33 inches, and opposable thumbs are unusual for creatures this old and this type of creature, not known to have opposable thumbs, but based on the depositional environment and the rocks and plant fossils contained within the rocks that these dinosaurs were discovered in, we figured out that this is likely a special adaptation for living in trees. These animals lived in a rainforest environment in what is now China. And this is one of my favorite paleontological reconstructions I've seen in a while. I just think the staging and the color of this particular image is amusing.
Are our opposable thumbs due to the fact that we were once in trees?
You're going to have to ask an anthropologist about that.
Okay, all right. Thank you.
Another exciting piece of, well, I suppose glaciers aren't known for being exciting, fast-moving phenomena, but up here in Alaska at the Muldrow Glacier, which flanks Denali, the largest mountain in North America, it has been surging. So this glacier typically moves at about 2 meters, 0.2 meters a day, which is about, I think that's about 10 inches. No, it's less, even less than that. It's not very much. Glaciers typically move very slowly, and this one is no exception. However, it is one of the 1% of glaciers worldwide that surge. And the last time it surged was in 1956-57, where the glacier moves at about 100 times its normal velocity over the course of a couple months. So it's now moving at 10 to 20 meters today, compared to a normal 0.2 meters per day. And this is due to the amount of debris and meltwater below the glacier. So at the base where the ice meets the bedrock, which is several hundred to several thousand feet potentially under the surface of the ice here. This glacier is enormous. Here's a view from orbit. You can see the headwaters, that source of the glacier, I guess. All of this ice comes down from up here on the top of the Denali Massif and gets funneled into this valley here. This green outline here, this bluish green outline, is the extent of the 1956 surge. And this is where it was before the present surge. And now it's about here now, last time I saw. And that's what causes this sort of blocky, chaotic texture. Normally, the Muldrow Glacier is very smooth and is used for one of the main paths to ascend to summit Denali for mountain climbers. But this surge has rendered the surface untraversable and very chaotic. This is actually an audio recording device here, a microphone, we call it in the sciences. And they've been recording these sounds of the glacier surging. And you can find some of these recordings online. It's very, very interesting sounds.
You're not going to make the sound for us?
No.
Okay, Peregrine asks, what changed about the amount of debris, et cetera, that makes the glacier surge?
So in certain areas, just the amount of debris that gets trapped underneath the glacier is due in part to how the bedrock is shaped at the bed of the glacier. But more debris allows more water to exist underneath the glacier, and that lubricates the base of the glacier, which allows it to surge.
Cool.
So it's sort of a complicated and sort of self-feedbacking system. More water creates more debris, and more debris allows space for more water, which allows for it to surge. And then once it's done surging, all that water is mostly drained out, and then it moves slowly for the next several decades.
Actually, what is happening at the front of any surging glacier is you get a lot of stagnant ice.
Okay.
And what it does is it plugs up the plumbing system. And so the water that is traveling down not only under the glacier, but through the glacier has no place to go. And it builds up. And you can tell if a glacier is going to surge by flying over the top of it, and you're going to see lots and lots of lakes on the top of the glacier. And then when it's surging, then you're going to have a huge amount of water coming out at the front, because what is happening is that stagnant ice breaks up. And then the water will start going out. And then later on in the summer, what's going to happen is there is going to be a gigantic Yokalaup, or a large glacial outburst floods, when all of that the stagnant ice basically breaks up at the front. and the water that is held in the glacier will go out. And they're predicting that for the Muldrows midsummer. And then what will happen is the glacier will stop and then get back to its normal movement.
I would like to point out this image is from late last season. I'm going to say September or October. And what's interesting is you don't see big meltwater ponds in it. And this glacier is largely debris covered, even all the way down to the toe, actually extending pretty high up the flanks. So I don't know if, and it is interesting that it began surging in the middle of the Alaskan winter, relatively speaking, or spring. So yeah, I'm very excited to keep following this and see how it all unfolds.
Ellen asks, what would cause flooding downriver?
Oh, and all that meltwater that Scott was talking about escapes from underneath the glacier.
Yeah.
The river is then containing much more water than it typically does, and that generates flooding.
All right.
There's another interesting article that came out of Yellowstone on paleoclimate. Now, paleoclimate is the study of ancient climate, and some researchers, Kathy Whitlock from Montana State University, was allowed by the Park Service to go out onto Goose Lake here in the Middle Geyser Basin. If you're familiar with Yellowstone at all, this is the Grand Prismatic Spring, one of the largest and most beautiful hot springs in the world. And she went out into this lake in a boat and collected a 30-foot long sediment core from the bottom of this lake. And when you extract that sediment core and take it out, you can analyze the layers in the sediment to establish paleoclimate using things like pollen. And they found an elevation in the arsenic levels about 3,800 years ago, which shows they interpreted to be a shift in the hydrothermal activity. The pollen counts in this lake suggested that it was a dense lodgepole pine forest, but an uptick in hydrothermal activity rate here drove out, the lodgepole pines and created this sort of open landscape you see there now. There's a lot of grasses here instead of tall trees in this geyser basin. And future research will look at multiple lakes across the park to see how this trend of hydrothermal activity influencing localized climate and plant communities evolves with time.
Can you explain how arsenic is an indicator there?
It just comes from deeper within the earth. These fluids that are escaping from both shallow sources and deeper sources near the magma chamber below Yellowstone carry up arsenic from deeper within the earth.
I see.
I'm sure Scott knows more about that, or Clark probably both know more about that than I do.
Kathy Whitlock used to be a professor at the University of Oregon.
Is that true? No way.
She is one of the most outstanding palynologists in North America.
Paleontologist?
Cool.
Study of pollen.
Study of pollen.
Yeah.
Peregrine asks, since the trees still aren't there, does that mean the hydrothermal activity has stayed the same or similar since then?
Yeah, I mean, you can see the all this white stuff. There's travertine, there's geyserite, there's a variety of minerals here that are inhospitable for tree communities to live in. So yes, this area, also just the ground temperatures, all this fluid heats up the shallow ground surface, and it's often cases too hot for trees to survive very well. So yes, this is still a bad area for trees to live.
Bad area for trees. Okay.
Another piece of dinosaur news came out of the University of California Museum of Paleontology about estimates for T-Rex populations. They used a thing called Demuth's law for population density, which is not something I was previously familiar with, to estimate the global population of Tyrannosaurus rex. And this law basically states that the body mass of a creature directly relates to its population density. So they assumed an average T-Rex mass of about 11,400 pounds, and that using the law, that came to 1 T-Rex per every about 40 square miles, which means, given the geographic distribution that we know from fossils, gives an estimate of about 20,000 T-Rexes alive at any given time. And since they lived for about 2.5 million years, that gives a total for 2.5 billion total T-Rexes over their species existence, which is very interesting. And this is, of course, a rough estimate subject to preservation bias and a variety of errors that are inherent in estimating long dead creature populations.
A lot of T-Rexes.
It's a lot of T-Rexes. And now I'm going to get into the weeds of geochemistry a little bit. There was a new paper out of the University of Wyoming about the Cordilleran and Anatectic belt, which is something I had never heard of until I read this piece of research. So starting up here in British Columbia and extending down through Arizona and into Mexico is called the Cordilleran Anatectic belt, which is a whole suite of intrusive igneous rocks that are comparatively young. This is Eocene and Oligocene in age, so that's in the 40s and 30s million years ago. And these rocks are the results of melting within the crust. So most melt we think of comes from the upper mantle or the very base of the crust, but this is very shallow melting comparatively. And it would have melted at about a temperature of 800 degrees Celsius, which is very low, even for crustal melting. But this is aided by water within crust. So some of the thinking was as the Rocky Mountains were uplifted, what is called the Laramide orogeny, where this front of the Rocky Mountains was uplifted. The thought is that rocks containing muscovite mica were buried and altered in such a way that the water trapped within the mica sweated out. And this water causes melting by a process called flux melting, and this water lowers the melting point of rocks, which could have caused this crustal melting, which created these suites of shallow igneous rocks.
So it's a secondary result of that orogeny. And what caused, is it that it's that whole orange band that goes all the way from BC down to Mexico?
Yes.
What caused the orogeny? Or do we know that?
So this orogeny is the result of the Farallon plate subducting into North America. We do still have a remnant of the Farallon plate, the Juan de Fuca plate, which is currently subducting underneath the Pacific Northwest. Most of the Farallon plate, though, is hundreds and hundreds of kilometers deep in the mantle somewhere underneath eastern North America.
So sad to see it go. But this is the orogeny is when the Farallon closed up that gap and crashed into the North American craton?
That's correct.
Okay, well, that's fascinating.
Yeah, but what was really interesting about this particular study was that it was a class at the University of Wyoming. This lead researcher, James Chapman, had a graduate level class with one undergraduate student in it, and they sought out to answer this question. This study was a part of a graduate level course, and all of the students in that class became co-authors on the paper, and they were studying the geochemistry behind this rather unusual suite of igneous rocks.
And is there surface expression of those rocks? Or
Yes.
You probably said that at the beginning. But...
Yeah, they are sporadic throughout this orange belt here.
Got a really good question here, again, from Peregrine, who is a font of good questions, but this is always interesting. Maybe it's too technical, she says, but how can water lower a melting point?
You're going to have to ask a geochemist, but that's just how it works.
That's so critical to the whole story of plate subduction, and I've never been quite clear how it works. Scott, do you have an answer to that question?
That's one that I really don't have an answer to. So, Andrew, great news item. I love this.
Yeah, that's
it's very interesting. In case there's any doubt about water causing melting, this is verified by lab studies. We can heat up rocks and they melt when water is present at a lower temperature. Typically, rocks will melt, depending on the composition, sort of in the 1,000 to 1,200 degrees Celsius range. But 800 degrees Celsius is about the coldest level that rhyolite lavas can exist, and below that, they tend to be solid. But their shallow level combined with the presence of water allows them to melt at a lower temperature.
Peregrine says, I believe you.
So this is indeed a complicated geochemical story, and was a bit in the weeds even for me. Geochemistry is a very complicated, field.
Well, I appreciate your bringing that in. Those of us who've been following Nick Zentner and some of those conversations about the gradual accretion of the western part of the North America, that's a big piece of that story of how the Farallon plate was subducted. So thank you.
Yeah.
Ken of Brian is saying salinity changes melting and boiling points also, and has a link in the chat. How does salinity affect That's the first I heard of that.
Well, with water.
With water. Okay, I see. All right, thank you.
I can't remember if I have one more or not. Oh, I guess that was it. Are there any
That's it for
questions
questions.
about this research section of this month's Geology News edition? Anything at all?
Put it in the chat or raise your hand. Andrew, you have exceeded yourself once again with both a delightful and comprehensive survey of the month's geology news. And Sheila amplifies that as well. So I think, Carol, you can hit the record button